Okay, so after the marathon of the last lesson, let's hope this one's a little bit shorter. We're going to start our second part of graphing rational functions. And today we're going to talk about two special cases. One, when our degree of our numerator is one more than the degree of the denominator. We said earlier in a previous slide that that's going to create what's called a slant asymptote. And in order to find that slant asymptote, we're going to use long division. We'll get to that in a second. Let's first of all go ahead and find all the other things we've been looking for in our previous graphs. We have a vertical asymptote of 5 because we set the denominator equal to 0. So we get x equals 5. We have a y-intercept of 2/5 by setting x equal to 0. To find our x-intercept, we set y equal to 0, multiplying x minus 5 to both sides gets it 0, so we get 0 equals x squared minus x minus 2, which factors to x minus 2 and x plus 1, which gives us x-intercepts of 2 and negative 1. And then finally we'll tackle our slant asymptote. And I'm going to use long division. I could use synthetic, but I'm just going to use long because in some cases it won't end up nice, and this will be a good review anyways. We have x squared minus x minus 2. We take and say x times what is x squared? That's an x. We have x minus 5 when we multiply. And now we have to subtract, don't forget that. And when we subtract, both go to opposites, so this ends up as 4x minus 2. And then you'll notice x times what is 4x? That's a positive 4. So I get 4x minus 20. Now you'll notice this doesn't go in evenly, but that's okay, because what we're looking for is we're looking for the equation of a slant asymptote. And a slant is just a line. And y equals x plus 4 is the equation of our slant. So now I go over, draw my set of axes. I'll put an x-intercept at 2 and at negative 1. I'll put a vertical asymptote at 5. And I have the slant asymptote at y equals x plus 4, positive slope of 1 up 1 over 1. So it's going to create a line something like this. Now, based on some of our conversations already, I know that I have to approach these asymptotes. And also too, the slant asymptote only describes end behavior, what the line's doing as x goes to infinity and negative infinity. So I know this, I know it's got to go through these points here, like so. There's no other way this can really happen. And we're going to approach this here. Now since I have no x-intercepts over on this side of the line, then I know my second part of the graph has to be up here. We could prove that by plugging in a point and checking, but no need because I know that's going to happen. There's going to be nothing on this side because then it wouldn't pass a vertical line test. So that's all there is to that one. Similar situation here, let's just do another one for practice. We have a vertical asymptote at x equals negative 2 because I set the denominator equal to 0. We have a y-intercept at 3/2. X-intercept, if I set y equal to 0 and multiply by x plus 2, I have x squared plus 3 equals 0, so x squared equals negative 3. That's a problem. There's no x-intercept. And then we have to find our slant. So again, I have x squared. I'm going to put my placeholder of 0x plus 3. long division with my x plus 2. That's an x and an x squared plus 2x. Subtract negative 2x plus 3. And multiply, I get a negative 2. Have a negative 2x minus 4. And again, we said we don't need to worry about the remainder, so I'm just going to leave it. X minus 2 is our slant. Once again, draw our axes. We have a vertical asymptote at negative 2. At x minus 2. We have our slant asymptote up 1 over 1. I have my y-intercept of positive 3, or no, 3/2, sorry. Puts me right around here. So again, I know what this graph's going to look like because I know for a fact there are no x-intercepts, but it goes through this point. Has to do something like this. And it goes to the right forever, so nothing's happening down here. Wouldn't pass a vertical line test. And then over on this side, since there's no x-intercepts, I know it has to exist down here because it's never going to cross that line. So now, once again, we have a situation where degree on the numerator is 1 more degree on the denominator. We're going to have to do our long division again, except this time it looks like we may have to factor the top to get our x-intercepts, which is not a problem. We have a vertical at negative 7 over 2. We have an x-intercept. Set y equal to 0, so 0 equals 2x squared plus 5x plus 2. You can do a 5-step or guess and check. We got a 2 and a 1. So I get negative 1/2 and negative 2 for my x-intercept, so y-intercept of 2/7. Slant. Let's go over our long division once again. 2x squared plus 5x plus 2. We got 2x plus 7. We go x, which gets me a 2x squared plus 7x. Subtract negative 2x plus 2 and multiply by negative 1, and there is our slant. Go through the graphing step. In this case, x-intercepts of negative 1/2 and negative 2. Vertical asymptote from negative 3.5. And a y-intercept of 2/7. And our slant once again was x minus 1. Similar to a couple other examples we've already had. Got to go through this point, which means it's going to go up here, come down, up through these points, approach that line. Nothing on the left side, so it's got to be down here. Okay, now in this case you'll notice we have what would be, if I multiplied this out, what looks to be something like a situation where my degree in my numerator is 1 more than my degree on the denominator. However, because we have an x squared and an x. However, you also notice that we have a reduction right here. And in all cases, you probably want to look to see if there are any reductions right off the bat. Because if something reduces, what's going to happen is you create something called a hole. Hole when reduction occurs. Because it's like when you plug back into the original equation and something doesn't work, we call that an extraneous answer. Well, this is kind of like an extraneous point. It's one place in the graph where there's nothing that exists. It's not an asymptote because when we rewrite this equation, that x plus 3 is no longer in there, so you don't see it. It graphs actually like a line because what's left is y equals x minus 4, which is the equation of a line. So I go down 4 and then up 1 over 1. But the deal is here, this graph is all good until I get to x minus 3. When I get to x minus 3, I have what's called a hole. So at x equals a negative 3, there's a hole. But what I need to do is I need to find my y value. My y value is going to occur in this graph when x equals negative 3. We pretend like it's there and plug it in. We get negative 7 out. So at negative 3, negative 7, we get a hole. So here's negative 3, 4, 5, 6, 7. I put an open circle and I continue to draw my graph. So no asymptote, just a hole in the graph. And that's going to happen every time we get a reduction. We call this a non-continuous point, or a point of discontinuity also. So we go through this problem, and again it's kind of a tip-off into what we did on the last problem. Should probably take a look and see if that factors, which it does, to x plus 2 and x plus 3 over x plus 2. So it's clear to see this is just like the last problem. We have x plus 3 after we reduce is equal to y, and there's a hole at x equals negative 2. And if we want to find the y value of that hole, we pretend like that negative 2 is there, plug into the remaining equation that's left, which is x minus 3, and end up with 1. So we have a hole at negative 2 and 1. And then I'll go ahead and graph this line. So here's my graph. Go up 3, and then up 1 over 1. And we end up with a graph that looks something like this, but at 2 of the negative type and 1, we have this open circle, and we draw the graph. Are they always going to be lines? Not always. But in the cases we've done, yes they are. So let's take a look at this. It looks like there's a lot of factoring to do here. I'm going to real quick go ahead and go through and get some of that done. We've got 2x, an x, need a 1 in the middle, so we need a 2 and a 3, and that's going to be a negative here and a positive here. In the denominator, I pull that x out, and then I need a 1 in the middle, so that's plus 3 and a negative 2. So in this case, we have factorable terms and a reduction. So I'm going to have a hole. Let's do that first. Get a better color too. We have a hole at 2, and then what's left, I have 2 times 2 plus 3 over 2 times 2 plus 3, oops, 3, which gets me 7 and 10. So I have a hole at 2 and 7/10. We'll use that later. Now we have some intercepts. Since this reduced out, The only thing I'm looking at now is the equation of 2x plus 3 over x times x plus 3. My intercepts in this case are going to be at the following spots. You'll notice in this case that when I plug a 0 in for x to get my y-intercept, this whole denominator goes to 0, so there is no y-intercept. No y-intercept, which is going to make a lot of sense because when I set my denominator equal to 0, we have vertical asymptotes at 0 and -3. So if there's a vertical asymptote where the graph is completely undefined, it makes sense there's no y-intercept. And then we have an x-intercept at -3/2. So now we can go ahead and graph. We have this vertical asymptote at x equals 0. We have another one at x equals -3. We have, actually in this case, we have a horizontal asymptote. Forgot to even do that one. Since we have degree of the numerator is less than the degree of the denominator, that's at 0. So I'm going across here. Remember, this defines end behavior only. We have an x-intercept of -1.5, which is right around here. And then we have a hole at 2 and 7/10. So 2 and 7/10. There's a big old hole right there. Okay, which kind of gives away this right side of the graph. I know it's got to be above this line because it's not going to cross. So this has got to probably do this. The middle I have no idea what to do with, and this side I have no idea what to do with. So I'm going to have to plug in some points to this function right here. Let's take f of -1, f of -2, and then we'll have to go something over here, f of -4. When I plug in f of -1 to this equation, I get a positive over a negative times a positive, which equals a negative. So at -1, this is down below, goes something like this. At -2, I get a negative over a negative and a positive, which equals a positive. So this has got to come up. And then at -4, I get a negative over a negative and a negative, which equals a negative. So this is going to be down. And that's all she wrote. As promised, it's a little bit shorter than last time. So write out your lesson summary and do your Connect Ed, and we'll chat more tomorrow.